So, if you haven't heard of Kaggle, I would check it out. Kaggle is the go to community for data scientists. It consists of competitions that fall into two main categories: knowledge based competitions and reward based competitions. Obviously, they both give you a substantial prize in the end. Uh, so, we will be doing Kaggle's most popular competition, and we'll try to succeed in our score while not falling into some common pitfalls that competitors fall into while trying to get a score above a certain threshold. So, what does the Titanic have to do with cryptocurrency? Well, before we answer that question, it's important as data scientists to evaluate two things in this case. The first one is the broader context of our data set. In this case, it's what is the historical relevance of this event or the Titanic? And we want to do this sticking with the theme of extracting all value from our data, because as senior data scientists, we should think about extracting all of the value from our business's data. And obviously, in this case, we don't have some great cryptocurrency blockchain data that we want to make public at the moment. And instead, we're trying to find value from data science's most popular data set. And we should also think about in this data set what was the root cause of the problem? Why were there maritime casualties? And so the historical relevance of the Titanic was that it was the largest and most luxurious ship of its time, making it incredibly popular amongst the most wealthy in Britain and really other parts of the world. We see that there are passengers that got first class tickets that came from all areas of the world. It also had several new technologies. It had wireless technology that allowed for Morse code messaging over long distances, and it had some technologies that would enable the boat to float in case of certain water breach events. And then it was also part of a broader migration to the New World, and when it sank, its sinking accelerated Navy safety regulation. And so, why did the Titanic sink? Here we'll do a brief root cause investigation. And so, investigations on either side of the Atlantic found that there were an insufficient number of lifeboats, basically lack of resources, speed was excessive, and complacency. The ship was thought to be unsinkable. So another way you can say the Titanic sank was because of normalization of deviance. Actually, this was a term created in relation to shuttle Challenger in the 1980s by sociologist Diane Vaughan. And in that case, engineers warned O-rings could cause catastrophic malfunction, and management culture around safety was relaxed due to urgency to take flight. And here we see the deviation spiral. Essentially, what happens is there's some sort of deviation that occurs and the new normal exists. And because there's no failure, people find it okay to continuously deviate into normals that are actually worse than the previous normal. And this is what's known as the deviation spiral. And so you may be asking now, how is the Titanic related to cryptocurrency? Well, cryptocurrency is currency. And so how is the Titanic related to currency? Well, we know that cryptocurrency is a futuristic form of currency. Let's look at the current version of currency. And so this is currency today. And obviously, this looks kind of familiar. It looks a little bit like the iceberg. And so a lot of people may know what this is, and a lot of people may be asking it, well, is this an iceberg or what is it? And so this actually is currency today. And you can go to this URL to see what this is. This is what we call Federal Reserve M1. So now you may be asking yourself just who or what is the Federal Reserve M1 and why is there such a sharp increase in spring of 2020? And so whenever we want a factual answer to a question, a good resource to go to is perplexity.ai. And so we'll ask those two exact questions. And so we find out that the Federal Reserve is the money stock and it includes currency and circulation. And the sharp increase in M1 is due to COVID pandemic in response to the Federal Reserve. So there's a growth in M1 aimed at providing liquidity and support of the economy during a period of severe disruption. So the next question I asked was, what is the impact and increase of M1 on the economy? And when the money supply increases, it typically lowers interest rates, which encourages investment and stimulates consumer spending, which leads to an increased business activity, higher demand for labor, and a rise in production. However, an excessive increase in the money supply can also lead to inflation as the demand for goods and service rises, causing prices to increase. So the statement from the Federal Reserve is in line with this. So I guess the next question to ask for around the people of the world, is this a glacier? And in a way, it kind of is, because without a doubt, we have seen inflation in various places. So here, this article mentions that inflation is in fact a setback. So, maybe that's currency today, but it's also a glacier. And so is there a possibility that this deviation spiral is relevant to our current financial system? So what does this have to do with cryptocurrency? Well, some in the industry are saying that Bitcoin was created for a moment like this because, in fact, in the genesis block of Bitcoin is the phrase "Chancellor on brink of second bailout for banks," which is an homage to the government bailouts in 2008 and the last great financial crisis. The call out is a subtle need for a sovereign form of money without a central intermediary, in this case, the Federal Reserve. And as the U.S. government, the Federal Reserve, turns to slashing interest rates, passing large stimulus packages, and infinite quantitative easing, Bitcoin will soon do the opposite in the next Bitcoin halving. The contrast could not be more stark. So if you're interested in buying Bitcoin, these are two exchanges that you can use to buy. They are both very dependable and reliable, and you can feel safe either holding your crypto on either of these exchanges or moving them off, and you can trade them 24/7, these assets, and they offer other services as well. So now for the machine learning part of this, we're going to break it down into 7 key steps. For the machine learning part, we'll be using Jupyter notebooks and writing in Python, and be relying on the pandas library for data wrangling, NumPy for some numerical analysis, and sklearn for our machine learning tools. We'll be splitting up the machine learning part into 7 steps. The first step of which is problem identification. And so for this step, it's already defined for us by Kaggle, and inherently we're predicting life or death for passengers on the RMS Titanic based on the attributes that exist within the passenger data, like name, age, gender, socioeconomic class, etc. Machine learning step number 2 is data collection. And this step is also straightforward because Kaggle provides us with our data. And so our training data set has our training data set has 891 records, and our test data set has 418 records. And we'll keep the training data set separate from our test data set for the sake of the Kaggle competition. For this data set, our data preparation step will consist of feature engineering, which means that we'll be transforming our variables to make them in a form that's able to be consumed by our machine learning models as inputs. And we don't need to do any other data wrangling, specifically, some row-wise data wrangling, because our data is in the correct form as far as our machine learning observations go, and we have all of our data in one place. So we essentially need to go column by column, variable by variable, ensuring that our data is good and those variables are useful for the machine learning model. In this case, it means we'll be handling missing data, we'll be transforming continuous variables or numerical variables, and we'll possibly be recoding categorical variables. And so our first variable that we have is name. And so for this field, every passenger has a different name, and it's essentially a categorical variable with a lot of different categories. And so to get a useful category from it, we'll be splitting up the parts of the text that are in their name to extract the title. Things like Mr., Mrs., Miss, etc. For a second variable, gender, it's in a good form already. We'll just make it numeric so that it's more efficient for our ML model. For passenger class, there is no transformation necessary. For age variable, we take for missing values within that variable, we take the median of those age values by the passenger class, and we use the median age by passenger class as the passenger's age if they don't have one. So our first continuous variable that we come across are the ages. And so for this one, it looks like it's skewed to the right and skewed towards higher values. So to turn this into a useful variable, we'll transform it into a categorical variable where the categories make logical sense, and we'll have it be age categories like child, teen, young adult, adult, and elder. So our next two variables are numeric variables that separately represent the number of parents or children, and the other one represents the number of siblings. So for that one, we just add them together to get the total number of family on board. Our ticket variable we used to transform into a couple of numerical fields where if the ticket's alone, we denote that. And essentially, if the ticket's not alone, we have another field that has the count of passengers that have that same ticket. And then we also were able to extract another useful categorical ticket code field by putting in low category ticket prefixes into different buckets based on their likelihood of those ticket prefixes surviving based on their aggregate survival metrics. And so in this way, we essentially got rid of the groups that had a low amount of instances and instead turned them into groups that had a lot of passengers that existed within that bucket. And so for another continuous variable, fare, we transformed it by looking at some different price levels and that existed, and essentially just rounding off those price levels and then breaking up into 4 different buckets. In our cabin field, we did something similar with ticket code, where we reduced the amount of cabin codes for cabin by grouping together cabin codes that had a low amount of instances by some logic. And then for our embarked field, for people who had embarked field missing, we gave them the most common embarked point in Southampton. So now that our variables or our features are fit for a form to be consumed by our machine learning model, we just do some last couple steps in that we drop our unnecessary variables. We turn our categorical variables into dummy variables so that certain models can just consume them faster. And then we split up our data set back into the Kaggle training and Kaggle test data set that existed before. And we scale the values so that some of our models aren't affected by the continuous variables of different ranges. And we do some formatting of some of our data type. So now that data preparation step is done, we can move on to a model selection. And for this step, we're going to be selecting our models based on what we want to essentially teach in this post, and that's ensemble methods. And so why are we picking ensemble methods? Well, a significant number of Kaggle competitions are won by ensemble methods, and ensemble methods combine multiple models to produce more accuracy. They average out errors and could reduce risk of overfitting, which is a substantial risk on this data set in particular. And with ensemble methods, different parts of the ensemble can perform better on different subsets of the data. They're also more robust to noise and outliers, and they can be used when scaling computing power, like if you're moving to multi-GPU based cloud resources. A lot of these models can easily be scaled up to analyze large amounts of data. And so the models that we'll go over are two tree-based boosting models, AdaBoost and XGBoost. Our tree-based bagging model, Random Forest. Our model that's different from those, the support vector machine or hyperplane model, and our voting classifier model. Now that we're done with model selection, we'll move on to machine learning steps 5 through 7, which is essentially the model training and the hyperparameter tuning and model evaluation in between coming up with these models that we've selected. Our first model that we'll go over is XGBoost, and XGBoost is a tree-based boosted ensemble, which means it builds trees in sequence And with new trees, it focuses on training instances that were misclassified by previous trees. And XGBoost has a lot of parameters that allow for more nuanced adjustments on different data sets. So we train and do parameter tuning with the use of grid search CV, which allows us to put in a grid of parameters and have the training model exhaustively go through all those sets of parameters to find the best model and the best set of parameters. And in this case, it finds it and it gives it to us. And we also can see the most important features that are used in the XGBoost model. And this model gives us actually a really high score on our training data set at 90%. But then later we see on our test set, we get something like 76%. And so this model clearly overfits. So the next model that we'll go over is AdaBoost. And AdaBoost shares a lot of similarities with XGBoost in that it's a tree-based ensemble method and that it also builds trees in sequence. The difference between AdaBoost and XGBoost is AdaBoost builds weak learners. So instead of complex trees, it builds simple trees or stumps. You could call them weak learners. And in this case, our new trees focus on examples that were hardest to be predicted by the previous learner, and misclassified training samples are more likely to be picked up by the new learner in the next round of training. So in terms of how it handles misclassification and loss, it's a little bit different than XGBoost, and it's very different because it builds not complex learners, but simple learners in the forms of stumps. And so AdaBoost gave us a not as good a result on the training data set, but the result on the test data set was the same as XGBoost. So this shows that it's just as good. It's a more general model, and it's obviously performs just as good in our evaluation on the test set. But they're still overfitting in that it doesn't perform as well on our test set as it does in our training set at a significant margin. And so our third ensemble method is our first bagging ensemble, which means that instead of trees being built in sequence, they're built in parallel using different samples of data, and trees are built to their full depth, unlike the AdaBoost, and trees are averaged at the end to reduce variance. So yeah, the key difference here is that trees are built in parallel and then they're averaged at the end to reduce variance, which makes it a bagging method and not a boosting method. And so this is our best performing ensemble method in that it has the highest result on our test data set. And the highest result on our training data set as well. And so our next model for control will be the support vector machine. And support vector machine is not an ensemble method. It's actually very different than a tree-based ensemble in that it uses a hyperplane that represents the largest separation between the two classes. And this will be a good complement to a tree-based model in our final voting classifier because it is a different type of model. And there's different hyperparameters that are involved in the support vector machine. The most important of which is the kernel, which essentially means if your support vector machine will be linear or higher dimensional in nature, which there's obviously polynomial kernel, and then RBF, which is also a higher dimension kernel like poly. And so the SVM gives us a very good result similar to our random forest in that it gave us it gave us 84% on our training data set and 77.7% on our test data set. And so our next model will be a voting classifier model, which means that we'll be grouping multiple models and having them come up with their predicted values for the data set and then have them all vote based on what they have as a predicted value and have those predicted values then vote and come up with the final predicted value. And so here we can basically essentially combine 4 models and have them all vote, or 3 models. Our final model is our voting classifier, and so our voting classifier combines our 2 best performing models, support vector machine and random forest, and has them both individually vote for a label for a given observation and have those votes basically decide our final output label. And so in this case, we're combining 2 models, but you can always combine many more models using a voting classifier. And we test some correlation between our models and find that they are well correlated, but not perfectly correlated. So combining them in a voting model will provide some value because they are not perfectly correlated. And when we combine them, we get our final best result, which is our model that gets a 79.9% accuracy. So 80% is kind of the definitive high score in the Kaggle Titanic competition. Models that fall above 80% make either one of 2 typical mistakes. They either use a lot or little of the test records in training, or another less common mistake is that they use information about the families and the passengers that exists after the fact, like whether or not their family survived, whether or not they had all their siblings survive, and they use that information to give more knowledge to their machine learning model in training that inherently just exists in the test data set, or they only get from knowing what happens, after it sank. And so that's typically not obviously how a machine learning problem would exist for an organization. They are inherently trying to predict things that they don't know about. And so that's, I guess, brings the final notes about the ML exercise, that obviously there are a lot of limitations to this historical data set. And this was a very fun exercise, but it's obviously very probable that and that brings me to the final notes about the machine learning exercise, and that, it was very fun to work with this historical data set, but obviously uh, this model that we created will never be able to be applied to any incoming or new data. And obviously, we didn't do much data and preparation or data engineering with this in this exercise, but the data engineering is a very involved part of data science, and the intuition experience that comes from splitting up your testing data set, training data set, and working with different data sets is incredibly valuable. And so finally, I want to end by saying happy 15th birthday to cryptocurrency. This time of year, 15 years ago, the first block of Bitcoin was mined. It was called the Genesis block. And as we can see, the trajectory that Bitcoin has taken has been nothing short of amazing, and I think it's only going to be nothing short of amazing in the future as well. Thank you for listening to this first post, and stay tuned for the next. Thank you.